Oh, sorry. My computer's kind of laggy there for a second. Sorry about that. Welcome to this video. Oh, sorry. Give me a second. Okay. I don't have to wear the. Well, okay. Never mind. I don't want to get in trouble. Maybe I should just start this video over, right? Welcome to this video. It's about solving logarithmic equations, right? It's kind of introduction to solving. We'll get into a lot more fun stuff next week when we do applications. But this is the culmination of all the logarithms we've been working with, right? This is where all the splendor and the beauty of logarithms come into play, is the solving and then the applications. All right, so this is by far the apex of the quarter and probably the year, honestly, because we're working with logarithms. So we have our guided notes. If you don't have your guided notes, make sure you get them out so you can follow along. Hopefully this won't take too long as the other video. Sorry if it does. It's just kind of the nature of the beast with logarithms, honestly, especially when we're doing a lot of practice. Okay, so solving logs. We're going to be solving exponential equations by using logs, right, because they're inverses. And we're going to be solving logarithmic equations using exponents. Right, so vice versa, we're going to go both directions. One thing you need to know first, or a couple things, they're called the properties of equality. Right, so there's a property of equality of an exponent and properties of equality of logarithms. And essentially what it says is with an exponent, if b to the x is equal to b to the y, then x has to equal y. Okay, the formal statement is b to the x equals b to the y if and only if. If and only if. That's the formal statement. So b to the x is equal to b to the y if and only if x equals y. So this is only true if this is true. Right? In math, if and only if is a very, very descriptive statement, even though it doesn't sound like it. It basically sets up, it's either this way or no way. That's basically what it's saying. It's either this has to work or it never works. Okay, so it's actually kind of nice in math because it makes the proofs a little easier. You only have to prove one thing. In mathematics, when we write if and only if, mathematicians tend to shorten it to IFF, if and only if. Anyways, that's just a little nice bit of trivia for you. But it kind of makes sense. For example, if I have, what did I have on paper here? If I have 3 to the x power is equal to 3 to the 5th power, well then what does x equal? Well, I'm trying to solve for x, right? Well, what does the equal sign mean? Equal means same on both sides, right? I mean, 2 equals 1 plus 1. It's the same on both sides. It's written differently, but it's the same on both sides. So here, equals. Is the base equal to each other? Yeah, we're good. So since the base is equal to each other, we move on. Are the exponents equal to each other? Well, if this is true, then they have to be equal to each other. So we set the exponents equal to each other. Oh, hey, there's our answer. All right, so property of equality. If there's an equal sign, everything about it has to be equal. The base has to be equal, and the exponents have to be equal. Well, the base is already equal. We're good. So the exponents have to be equal, and we just set them equal to each other. Right? And it so happened we didn't have to do anything else. Same with logarithms. So for example, log base b of x is equal to log base b of y if and only if x is equal to y. Which makes sense. What did I have on paper? So if I have log base 4 of x is equal to log base 4 of 7, and I want to find out what x equals. Well, are the bases the same? Well, first off, you can even say, is a log the same function as a log? Yeah. Log is a log and a log are the same function. Okay. Are the bases the same? Are they equal? Yep, we're good there. Is what we're taking the log of equal? Well, we don't know. But in order for this to be true, they better be equal, so we set them equal to each other. And that's your answer. Okay, so property of equality. Now it gets a little bit tougher than that, obviously, but that's what the property of equality is saying. Okay. So let's move on. We got, there's 3 different ways of solving. There is using properties of equalities that we just talked about. There is converting to the inverse function. And then there is taking the inverse function of both sides. We are only going to do, in this class, we're only doing properties of equality, and we're only doing converting to the inverse function. We're not going to do taking inverses of both sides, because, in fact, taking inverses of both sides forces you to convert. So you're adding in an extra step. Okay, so we're not going to do it. I used to teach it, but actually one of the other teachers here, Ms. Kirkham, sorry, I don't know why I went brain dead. Don't tell her I went brain dead. Ms. Kirkham showed it to me. I was like, oh yeah, no duh. Like it makes complete sense, but I'd only ever been shown how to solve by taking inverses, not by converting. And I think converting is easier, so that's what we're going to do this year. Okay, so here we go. Equality properties. We have 100 to the x power is equal to 1 over 10 to the x minus 3 power. Okay, so equality property says if the bases have to be the same or have to be equal, and the exponents have to be equal. Well, the bases aren't equal, right? Is there a way I can make the bases equal? Well, you got a bunch of zeros, and I think you can see it, right? They're both not even, well, they're technically factors of 10, but you can write them as 10s. So 100 is 10 squared. So instead of writing 100, I'm going to write 10 squared. And 1/10 is, 10 to the negative 1 power, right? The negative 1 power creates the reciprocal, it flips it. So if I have a fraction and I want it not to be a fraction, raise it to the negative power so I can take the reciprocal. And then to the x minus 3 power. Are the bases the same now? Yeah. Okay. Now here we have a power of a power. So when I exponent an exponent, I multiply. So this is 10 to the 2x equals. Here, power of a power, so I multiply. Negative 1 times x is negative x, and negative 1 times negative 3 is positive 3. So 10 to the negative x plus 3. Now this is easier to see that the bases are the same, or equal. Well, the bases are the same, so in order for this to be true, the exponents have to be equal. Well, set them equal to each other. So I add x to both sides. 3x equals 3. Divide by 3 both sides. X equals 1. Plug it back into the original. Make sure you're not messing up anything. Right? Taking a log of 0 or getting a negative answer, things like that, right? Or not negative answer, but getting a negative base when you get a positive base, things like that. Right? Well, we don't. So x equals 1 is our answer. Okay. Let's do property of equality with logarithms. Got natural log of 4x minus 7 equals natural log of x plus 5. Okay, with natural log, what's the base? I can almost hear you through time into the past of how loud you yelled, base E. I'm so proud of you. Okay. So we're taking a log of both sides. Okay, that's equal. The base is the same, so that's equal. So in order for this to be true, what I'm taking the log of has to be equal. So we set them equal to each other. Get x by itself. So I'm going to subtract x from both sides. Add 7 to both sides. Divide by 3 both sides. X equals 4. I'm going to plug this back in to see if I get a log of a negative, if I'm taking a log of a negative, or if I'm taking a log of a 0, right? Because you can't take a log of 0 or negative for now, right? Let's see, plug in 4. Nope, no negative. Plug in 4. No negative, no 0. We're good. X equals 4 is our answer. Okay, so that's a couple of examples on how to do equality properties. We're going to do more of that when we get to do all the examples, but I'm just going to kind of going through from front page to back page. Now here, let's do this. 2 to the x is equal to 7. So when we get x by itself, we want to solve for x. The bases are not the same. Can you think of a way to get 7 to look like a 2 with exponents? Let's see. 2 to the first is 2, not 7. 2 squared is 4, not 7. 2 to the third is 8, not 7. We can't. Okay, well, we can, but it's a crazy decimal, and that's actually what we're finding out. So what we're going to do is we're going to convert. We're going to convert this exponential equation to a logarithmic equation. So converting, remember, base stays the same. What was outside of our operation, or outside of the function, is now inside. And what was inside the operation, or the function, is now outside. So x is equal to log base 2 of 7. That is an answer. That's actually the exact answer. Because log base 2 of 7 is an infinite decimal. You can't write it properly. So this is the exact answer. For this year, we're going to have you actually, to test you on your change of base formula, okay, we're actually going to have you figure out this decimal. Okay, not the whole decimal, obviously, because you can't. But we're going to have you find out the answer to 3 decimal places. We're going to have you round to 3 decimal places. So let's see. Remember our change of base formula? Learned it, well, not last week, right? It feels like last week when I'm making the video. We learned it about 3 weeks ago, right? When you're watching this, probably. So change the base formula. We change the base of our logarithm to whatever we want. We tend to pick natural log or common log because that's what the calculator has. Now, if you have a cool calculator, like my $10 one from Walmart, it can take the base log of anything you want. If you don't, I don't know what to tell you. Use change the base formula. Okay. So I'm going to change the base to natural log, to base e. What you're taking the log of is in the numerator. The base is in the denominator, right? So still, it's kind of like still the base stays the same because it's in the base of the fraction. But kind of, that's a stretch there, right? Equals x. And then type this in your calculator. So let's see here. Natural log of 7 divided by natural log of 2. So x is approximately 2.807, right? To 3 decimal places. And there's your answer. Okay. Now enjoy this while it lasts, right? I'm only doing fractions. I'm only doing decimals for this quiz. Right? I'm going to fight it on all the other ones. So enjoy it while it lasts, working with decimals. All right, let's do another one. We got log base 2 of 5 to the x minus 17 is equal to 3. Okay. Is the base of the log the same as the base of the log? No, because there's no log over here, right? So since there's no log over here, we can't do the equality property of logarithms. So let's convert. We're going to convert to its inverse, right? The exponential. So remember, base stays the same. What was outside of our function is now inside, right? Because it's an inverse, it's just opposite. What was inside our function is now outside, just the opposite. And now we simplify a little bit. 2 to the third power is 8. Add 17 to both sides. Divide by 5 both sides. So 5 is equal to x. If I plug that back in, am I going to get a negative number or a 0 in the logarithm? No, I will not. So 5 equals x is our answer. Okay, so not too bad. Let's go to more of a fun one, all right? Common log of 2x plus common log of x minus 5 is equal to 2. Well, these bases are the same, but there's no logarithm over here. So we're going to have to convert. But remember, our definition of logarithms, b to the x equals y, converts to log base b of y equals x. Notice when we convert, we need one logarithm by itself. So I need to condense these logarithms into one before I can convert. So let's do that. Let's condense into one. If I add outside, then I multiply inside. Right? The exact opposite of this. If I multiply outside, then I add inside the exponents. Well, here, the exact opposite. If I add outside, then I multiply inside the function. So let's see here. Log of, sorry, that should be a bracket because I'm going to use parentheses again. Log, or common log of 2x times x minus 5 is equal to 2. Okay? Let's simplify this a little bit. Got common log of 2x times x is 2x squared. 2x times negative 5 is negative 10x equals 2. Okay, now we can convert. Let's convert. Okay, if there's no base, if it's a common log, no base, what base is it? That's right, base 10. Okay, so we got base stays the same. What was outside of the function is now inside it. What was inside the function is now outside. Simplify, 10 squared is 100. All right, well, let's see, everything's divisible by 2, so let's divide by 2 both sides. Make our numbers a little easier to work with. So here we got 50 is equal to x squared minus 5x. Oh, we got an x squared, quadratic, solved by factoring, everything on one side, 0 on the other. So I'm going to subtract 50 from both sides. So we got 0 is equal to x squared minus 5x minus 50. Factor this. So 0 is equal to, let's see, factors of negative 50 that add to negative 5. Probably 5 and 10, huh? Negative 10, positive 5. Set each factor equal to 0. X minus 10 equals 0. X plus 5 equals 0. Add 10 to both sides. X equals 10. Subtract 5 from both sides. X equals negative 5. We got 2 answers. Aha, but we got to check, right? If I plug 10 into the original, do I get any zeros or negatives? Nope. If I plug in negative 5 to the original, do I get any negatives or zeros? Oh, yeah, right there. 2 times negative 5 is negative 10. And negative 5 minus negative 5 is negative 10. So this is an extraneous solution. Negative 5 is an extraneous solution. Remember that from last quarter. It's a solution we get that ends up not being true. Okay? So just x equals 10 is your answer. All right. Now we just have, 10 practice problems. Okay, we'll get through it. I'll try to go through it as quick as possible. So we're going on 20 minutes now. Let's see. Let's change up the color here. We'll go with blue. The black you can see is starting to run out because it's kind of getting stuck on the board. So we'll go to blue. Let's see here. 243 to the negative 3x power is equal to 27 to the negative x minus 2 power. Okay. Is there any way to get these bases to look the same? Because if I can get these bases to look the same, then I don't got to take logarithms or anything, right? We can just use the property, the equality property of exponents. Well, let's see. 3 to the third power is 27, right? Because 3 squared is 9. Okay, So this I can write as 3 to the third to the negative x minus 2 power. Okay, I'm good there. Can I get 243 to look like 3? Well, 3 to the fourth power, 27 times 3 is 81. 3 to the fifth power, 81 times 3. Well, 1 times 3 is 3. 8 times 3 is 24. Oh! 243 is 3 to the fifth power. Oh. Okay, power of a power property. You multiply, so this is 3. 5 times negative 3x, negative 15x. 3 times negative x, negative 3x. 3 times negative 2, negative 6. Oh. Equality, sorry, hiccup. Equality property of exponents. The base is equal. That means the exponents have to be equal, so we set them equal. Now get x by itself. Plus 3 both sides, plus 3 both sides, or 3x, excuse me. This is a negative 12x equals negative 6. Divide by negative 12, divide by negative 12. X equals 1/2. And there's your answer. Okay, there's your answer. X equals 1/2. Can you see that? Yeah. Yeah, you can. Although the blue's running out too. All right, you know what we're going to do? Forgive me, but I'm going to take like 3 seconds, or about 10 seconds. We'll get a couple more markers. All right, because I didn't think they were all out. Give me 10 seconds. Sorry, took a little longer than 10 seconds, but I also got a green one, so. Oops. Okay, let's do the next one. 16 to the 2x minus 3 power is equal to 4 to the third power. Oh, that's so nice. All right, much darker than it was before. Can I get 16 to look like 4? Or even 4 to look like 16? Well, 16 is 4 squared, so I can write this like that, right? Power of a power, 2 times 2x is 4x. 2 times negative 3 is negative 6, equals 4 to the third. Okay, now the bases are equal, so the exponents have to be equal. So 4x minus 6 is equal to 3. Plus 6 both sides, 4x is equal to 9. Divide by 4 both sides, x is equal to 9/4. And there's your answer, 9/4. Okay. Let's go to the next one. Now, there's a bunch of different ways you could do this. It's super fun. Maybe we'll have time in class to do it. I'll show you all the different ways. Because you could have wrote 4 as 16 to the 1/2 power, right? Or you could have wrote 16 as 2 to the fourth, and 4 is 2 squared, right? Oh, isn't that fun? You just find so many different patterns. Okay, let's see. Log base 16 of 5v plus 6 is or minus 6, excuse me, is equal to log base 16 of negative v plus 6. Okay, we're taking a log of both sides, so that's equal. Right, the function's the same. The base of the function is the same. So that means what we're taking a log of has to be equal. So 5v minus 6 has to equal negative v plus 6. Add v to both sides. 6v minus 6 is equal to 6. Plus 6 to both sides. 6v is equal to 12. Divide by 6 both sides. v equals 2. Plug v back in to see if I divide by, or if I take the log of a negative or 0. I don't, so that's your answer. I'm going to try this other one down here. natural log of 2x plus 7 is equal to natural log of negative 4x minus 5. Sorry, I had some in my... we're taking the same function both sides. The base is the same both sides, right? Base e. So that means what we're taking the log of has to be the same, has to be equal. So 2x plus 7 is equal to negative 4x minus 5. I'm going to add 4x to both sides. So I get 6x plus 7 is equal to negative 5. Subtract 7 from both sides. 6x equals negative 12. Divide by 6 both sides. X is equal to negative 2. I got to plug in negative 2 back into the original to see if I take the log of a negative or 0. Plug in negative 2 here. What do I get? I get 3. If I plug in negative 2 here, I also get 3. They're not 0. They're not a negative number. So that is your answer. X equals negative 2. Right? Now we have 10 to the m plus 10 power plus 7 is equal to 89. Well, bases aren't the same, and there's no way to get them to be the same. But first, remember when we're solving, we do reverse PEMDAS. So we got to start with our add and subtract first. So I'm going to subtract 7 from both sides. So 10 to the m plus 10 power is equal to 82. Still, I can't get 82 to look like the power of 10. Well, actually, I can, but that's what we're trying to figure out. So I got to convert. So base of the logarithm, right? Base stays the same. So common log. What was outside the logarithm is now inside. What was inside is now outside. Okay, now I'm subtract 10 from both sides. So negative 10 plus common log of 82 is equal to m. That is your exact answer, right? But common log of 82 is an infinite decimal. So I want you to round to 3 decimal places. Okay, look at your directions. It says round to the nearest thousandths place if needed. We need to round to the nearest thousandths place here. So let's see. We got common log of 82 is equal to that minus 10. Is that right? Yes, that's right. So negative 8.086 is equivalent or approximately m. All right, to 3 decimal places. All right, let's go over here. I'm gonna erase our PEMDAS. So here we got negative 9 times 6 to the negative 3/6 power, or negative 3x power, equals 54. Let's divide by negative 9 both sides. So 6 to the negative 3x power is equal to negative 6, right? 54 divided by negative 9 is negative 6. Now these bases are not the same. This is positive 6, this is negative 6. Okay, and using exponents, we can't get negative 6 to look like positive 6. So we're going to convert. Right? Base of our logarithm is the base of our exponent. Base stays the same. What was outside of your function is now inside. What was inside is now outside. Okay, we're actually done here. Can you take the log of a negative number? No. So because you cannot do this, no solution. Okay, we could have actually been done up here. There is no exponent. There is no exponent that will take a positive 6 and make it negative. No exponent. Right? Because negative exponents, they take the reciprocal, right? You get the reciprocal, not an exponent. Or excuse me, not a negative, the reciprocal, you flip it. Right, so you could have actually stopped right here and just noticed that it's no solution. Okay, 4 more. Log base 8 of x plus 4 plus log base 8 of 6 is equal to 1. Right, we're not taking logs on both sides, so we got to condense and then convert. So I'm going to condense this into one logarithm. Base stays the same. When I add outside, I multiply inside. So 6 times x is 6x. 6 times 4 is 24, equal to 1. Convert, base stays the same. What was outside our function is now inside. And what was inside is now outside. 8 to the first power is 8. Subtract 24 from both sides. So let's see. 8 minus 24 is negative 16, equals 6x. Divide by 6 both sides. Negative 16 over 6 is equal to x. Simplify by a factor of 2, right? I can divide numerator and denominator by 2. So negative 8 over 3 is equal to x. So if I plug in negative 8 over 3 to x here, do I get a negative number? No, because 4 is 12 over 3, and it's bigger than negative 8 over 3. Right, so we're still going to get a positive number. So negative 8 over 3 is your answer. Okay. Where am I? Oh, right here. Natural log of x plus 5 minus natural log of x plus 4 is equal to 4. Ooh, this is a fun one. Okay. Got to combine into one logarithm. Right, so we need to condense and then convert because there's not a logarithm over here. Right, so we're going to have to convert. So let's see. If I subtract outside, then I divide inside. So it's x plus 5 over x plus 4. Okay, remember, all the positive logs are in the numerator. All the negative logs are in the denominator. That's the pattern that we found. Okay. Let's see here. Now I'm going to convert. What's the base of natural log? E. So I have base E. What was outside the function is now inside, and what was inside the function is now outside. This is where it gets fun. Okay, stay with me here. I want to get x by itself, right? Okay. Now we're going to keep e to the fourth as e to the fourth because it's an exact number, and we're not gonna get our decimal until the very end. If we get our decimal now, when we do more operations, it'll offset the decimal a little bit, right? So it won't be the correct answer. So we're going to wait to get our decimal answer until the very, very end. Well, to get rid of the x plus 4, to get x by itself, if I divide by x plus 4, the opposite, right, the inverse operation is times x plus 4. So I'm going to do that to both sides. So on this side, I have x plus 5. On this side, I multiply e to the 4th times x is e to the 4th x. E to the 4th times 4 is 4e to the 4th. Okay, so this is what I get. I want x's on one side, everything else on the other, right? I want x by itself. So I'm going to subtract x from both sides. And here, I'm going to subtract 4e to the 4th from both sides because it doesn't have an x. Okay, so I have e to the 4th x minus x is equal to 5 minus 4e to the 4th. How am I going to get x by itself here? Well, I can factor, right? They both have an x. They have a greatest common factor of x. So I factor out an x. I get e to the 4th. Or if I take one x out, I'm just left with e to the 4th. Negative x divided by x is negative 1. Okay, now I have x here To undo multiplication, I have to do division, so I'm going to divide by e to the fourth minus 1. Divide by e to the fourth minus 1. So x is equal to 5 minus 4e to the fourth over e to the fourth minus 1. That is the exact answer. Once again, we want you to approximate this to the nearest thousands, so 3 decimal places. So I'm going to type in my calculator. I'm going to do 5 minus 4e to the fourth equals, I get a number. You should get negative 213.3926001. It goes on for forever, but that's as many decimal places as the calculator gives me. And then I divide. I want to divide by this whole thing, not just e to the fourth minus and then minus 1. We're dividing by this entire thing, so we got to use our parentheses, right? Our organizational tools. So parentheses, and then, oops, not absolute value, delete. E to the fourth minus 1, close parentheses. Like that. Okay? You're dividing by the entire thing, not just e to the fourth. Equals. X is approximately negative 3.981. There's your answer. Okay. That's probably the hardest it'll get, honestly. Okay. So if you can do this, the test is going to be a breeze. Super simple. Okay, 2 more. Making better time than I did last video, right? Okay, so we got log base 6 of x plus log base 6 of x plus 5 equals 2. Condense and then convert. So base stays the same. When I add outside, I multiply inside. X times x is x squared. X times 5 is 5x. Convert. Base stays the same. What was outside the function is now inside. What was inside is now outside. 6 squared is 36. We got a quadratic, right? We have a squared, so everything on one side, 0 on the other. So 0 is equal to x squared plus 5x. Subtract 36 from both sides, minus 36. Now we got a factor. Factors of negative 36 to add to positive 5, plus 9, minus 4. Set each factor equal to 0. Subtract 9 from both sides, x equals negative 9. Add 4 to both sides, x equals 4. Okay, now we got to check. Plug in negative 9. Ooh, if I plug in negative 9 here, I'm taking log of a negative number, which I can't do. So that's an extraneous solution. Here, if I plug in 4, I'm good there. And I'm good there. Right? I'm not dividing, or I'm not taking log of negative or 0. So I'm good there. So 4 is your answer. Negative 9 is an extraneous solution. It's not a solution. Okay. Okay, last one. Log base 6 of x squared minus 1 minus log base 6 of 8 is equal to 1. Once again, there's not logs on both sides, so we can't use the equality property of logarithms. Oh, I always forget names. So we're going to condense and then convert. So base stays the same. If I subtract outside, I divide inside, so I got x squared minus 1 over 8 is equal to 1. Convert, so base stays the same. What was outside of our function is now inside. What was inside is now outside. 6 to the first power is 6. Now, to get x by itself, I'm dividing by 8, so I got to multiply by 8 both sides, right? Inverse operation, they undo each other. So 48 is equal to x squared minus 1. Plus 1 to both sides. 49 is equal to x squared. Square root both sides. X is equal to plus or minus 7. Right? When you enact the square root, you got to put plus or minus. Now, if I put in positive 7, do I get a negative number in here? Nope. If I put in negative 7, do I get a negative number? No. Right? Negative 7 squared is positive 49. In your calculator, if you type it this way, let me show you. Let's see, negative 7 squared. If you do this, if you just type it like you say it, you get the wrong answer. It's not negative 49. Right? It's x squared. X is negative 7. The entire thing is squared. All of negative 7 is squared. So how we type it is parentheses, negative 7, parentheses. The entire number is squared. All of negative 7 is squared. Right? Not just the 7. Oh. Anticlimactic, right? Equals positive 49. All right? The reason for this is because you are more intelligent than the calculator. Okay, the calculator is an inanimate object. It does what it's told to do. So you need to act more intelligent than the calculator. All right, the calculator is going to do what you tell it to do. It's going to do PEMDAS perfectly. So if you type in this, it's going to do its exponents before its minuses. So it's going to do 7 squared and then the minus. All right? So you got to type it to where an inanimate object, something that's a lot stupider than you are, you got to type it correctly so it understands you. Okay? So this is the whole thing squared. That's it for this video. I cut off 6 minutes. Aren't you proud of me? I'm sorry, right? Logarithms are just going to be long, especially because they're new. So we do a lot of practice. That's it. Remember, if you need help, if you need anything, I'm always here before and after school. Check your announcements in case I do have meetings. Right? I was going to say have a good break, but you're probably back from break when you're watching this. So have a good week or weekend.